Hello everyone. Am I audible? Have all of you muted yourselves? Have all of you muted yourselves? Okay. Am I audible?
Yes, ma'am.
Okay. So yeah. So let's begin. So I am Tanya. I'm one of the TAs assigned to the Aircraft Stability and Control course taught by Professor A.K. Ghosh. So we'll be meeting once every week to discuss the contents of that week and help you in solving the assignments. So for the first week and the second week, the assignment due date is on the same day. After that, it will be just the Wednesday after the week. Okay. Okay. So let's begin. So now we'll just go over a few concepts in week one. Before that, I think there were a few questions in week 0. So we'll just address those questions. So the first question was, which type of airfoil is suggested for a flying wing? Can anyone try to answer this? First of all, what is a flying wing? Actually, since there are just few of us here, can we all just introduce ourselves? So I'm Tanya. I'm a PhD student in aerospace engineering, flight mechanics specialization. And there are just few of us here. So can one of you just try to tell me your background? Just introduce yourselves. Yes, just anyone. Are you anyone from an aerospace background? Your voice is not clear. I'm not sure who's trying to speak, but your voice is not clear. Just a second. Can you try speaking up? Okay, no, your voice is not clear. Can you type it in the chat box? Anyone else? Okay. Hello, Sarthak. Are you from an aerospace background? What is your background? What are you studying? What are you pursuing? Okay, third year aerospace engineering. Oh, that's great. That's great. Anyone else wants to introduce themselves or just anything? Yes, yes. Yachit. I hope I'm pronouncing it right. Yachit, yes. Are you also from an aerospace background?
No, ma'am. I am pursuing electronics and computer engineering from Thapa University, Patiala. I'm a second year student.
Okay, okay. Nice, nice. Okay. Anyone else wants to introduce themselves? You can just put it up in the chat box if you're not comfortable speaking up. Okay. If not, so I hope all of you have gone through these questions, right? Week 0, week 1, and the questions. Okay. Hello, Nandini. Hello, Madhuri. Okay. A lot from electrical electronics. That's really nice to see. Nandini, which department are you from? Okay. Physics. Oh, that's nice. Okay, you can just go on introducing yourselves in the chat box. Okay, so let's just start with the first question. The first 5 questions were just to see what kind of knowledge you have already and to help us to get your caliber. Okay, so just answer these 5 questions with whatever knowledge you have. I'm sure the people from aerospace background should already have some idea. So which type of airfoil is suggested for a flying wing? So what is an airfoil? Can someone tell me what's an airfoil, especially the ones from aerospace, aeronautical? What is an airfoil? Is something wrong with your audio, Sarthak? I think it's with your audio. I don't think it's on my end. Can anyone else try speaking? I just want to confirm if it's from his end or my end. Somebody else, can you just speak up a sentence?
Yes, ma'am.
Okay, yeah. So Sarthak, I think it is a problem with your audio. Please try to fix it, or you can put up in the chat box. Meanwhile, can anyone tell me what an airfoil is? Okay. Matic says it's the most efficient shape to generate lift. Okay. Okay. So considering a wing, what is an airfoil?
Ma'am, if we cut the wing in the vertical direction, the shape we get is an airfoil.
Yes, yes, correct. So it says most efficient shape to generate lift. Yes, that shape is the one that we use in the wing. So it is just a cross section of the wing. That is an airfoil. Okay, and what is the flying wing? It's cross section. What is a flying wing?
The wing that are attached to the body that help the airplane to fly.
Okay, so in this case, I believe that the question says that the aircraft or the flying vehicle is just a wing. Okay, so it doesn't have a tail and the other structure. So it's just a wing. Okay, so now keeping this in mind, let's try to answer this question. Some of them already answered it, but let's go over it. So which type of airfoil is suggested for just wing alone configuration? Is it symmetrical, cambered, reflex, or none of these? So let's start with each of those airfoils and their properties. Symmetric airfoil. So this is, you need to bear with my drawing, it's pretty poor. Okay, so symmetric airfoil has the upper surface and the lower surface same, right? So it is similar. So and cambered, how is the cambered airfoil different from this shape? How would it be different?
थोड़ा नीचे से उठा हुआ होता है वो.
Okay, yes. Okay. So there is a curvature on the below surface, something like this. Okay. Again, bear with my drawing, it's very bad. And what is the reflex airfoil? Any idea what is the reflex airfoil? Anyone? Just try. This is the very first session. You don't have to worry about if it's the right answer or not. Just try. Have you heard of reflex airfoil? Diamond shape. Okay. Okay. I don't think no. Reflex airfoil is not a diamond shape. Yes, Sarthak is right. At the trailing edge, it's curved. So it's basically just the cambered, but at the trailing edge, you have an upper curvature. Okay, so it's like this. 1 minute. It's something like that. Right? So this is the reflex airfoil. Why do we have a reflex airfoil, Sarthak? Now that you know what a reflex airfoil is, you try to tell me why do you have this upward curvature? Okay, before that, the symmetric and cambered. Can you tell me what are the differences in the characteristics between symmetric and cambered airfoil? Somebody said airfoil is the most efficient shape to generate lift. Yes. So why do we have different shapes? Why do we have symmetric airfoil? Why do we have cambered airfoil? What is the difference? Both of them generate lift, right? But what is the difference between symmetric and cambered? Symmetric airfoil cannot generate lift in negative alpha. Okay, okay, okay. So let's just go look at the lift curve slope. Okay, so what was the lift curve slope? It is the slope between CL and alpha, where CL is the coefficient of lift and alpha is the angle of attack. Okay, so for a symmetric airfoil, the curve is something like this. All right. So at zero angle of attack, you have zero lift generation. At positive angle of attack, you have positive lift generation. If it's a cambered airfoil, how will this curve look? This curve, how will it look for a cambered airfoil? So this is for symmetric, right? So this is for symmetric. For a cambered airfoil, how would this curve look? The lift curve slope. It will start slightly behind origin. Yes. So this curve will just be shifted, like Sarthak said, just shifted before the origin. So it will be something like this, right? So this is for a cambered airfoil. what we can see here is that for zero angle of attack, you have some lift, right? So even if your airfoil or wing is attached at zero angle of attack, you have a lift generation. That is why the cambered airfoil, that is one property that is more beneficial for the cambered airfoil than for the symmetric airfoil, okay? Now, can you try to tell me what changes for a reflex airfoil? Why did we come up with the reflex airfoil? Symmetric airfoil produces lift at positive angles of attack. Cambered airfoil, we came up with it so that we can produce lift at even zero angle or negative angles of attack. Why do we need reflex airfoil? Like someone said, the answer to this question is reflex airfoil, but can you tell me why? Can you justify your answer? Or tell me what is the reflex airfoil? How is it different? Why did we have to create such an airfoil cross section? Anyone? Just try. Someone had answered. Third is the correct answer. I'm not sure who it was. Can you try justifying your answer? Sure who answered. Yes, Santosh, I think, had said third is the right answer. Third is the right answer. You're right. Can you tell me why? Okay, it's something to deal with the pitching moment, if that hint helps you in some way. Okay, so we will come back to this question once we deal with the Nishi concepts of week 1. Okay, just remember this, we'll come back to this question, right? Okay, next question. So these are the different kinds of airfoil. I just thought I'll put it up here. So this is the symmetric airfoil that we discussed. This is a low camber airfoil, the first one. So this is the low camber airfoil, right? So next is the deep camber, where the bottom surface is still flat. It still produces the lift at negative angles of attack. And then you have the deep camber, this one, right? So these two. Are you seeing what I'm writing on the screen? Because I'm not seeing it. You can see it. Just let me know if my audio or video. Can you hear me? So the internet connection. Okay, sorry about that. The internet connection is poor here. Okay, can you hear me now?
Yes, ma'am.
Okay, and is the screen visible?
No screen, madam.
I'm sorry, I didn't hear you. Can you see the screen? Can you see the slides?
No, ma'am.
No. Okay. Okay. 1 second. Just a minute. I'm sorry about this. Okay. I think it's visible now, right? Yeah. Okay. So the first one was a low cambered airfoil. So this is the low cambered airfoil. The other two are deep camber. Both of them produce a lift at negative and zero angles of attack. Then you have, this is your reflex airfoil, right? So this is your reflex airfoil. Here it says the reflex trailing edge wing section. That is what Sarthak, I think Sarthak had said that. I'm not sure who said it. Okay, so Sarthak had said that the trailing edge is curved upwards. Then you have this last one. Can anyone tell me what this is? This airfoil, this last one, this one. What type of airfoil is that? So you have low camber, deep camber, symmetric, reflex. What is this last airfoil?
Ma'am, I can't hear your voice, ma'am.
Okay, okay, I'm sorry. Can you hear me now? Can you hear me now? Can someone confirm Okay. So you're able to hear me, right? Santosh? Santosh, am I audible? Okay, can someone else confirm? Am I audible?
Yes, ma'am, you are audible.
Okay, thank you. Thank you very much. Okay, so can you tell me what the sixth airfoil is? It says there GAW, this is the sixth airfoil. So you have symmetric, low camber, deep camber, reflex. What is this last airfoil? So you can see how it is different from the other airfoils is that the top surface is slightly flattened. It is thicker and the top surface is slightly flattened. Any guesses? Okay, so this airfoil is called a supercritical airfoil. Supercritical. Have you heard of it? The ones from the aerospace background, have you heard of it? Supercritical airfoil? Okay, so next class, just look up the supercritical airfoil. It's used in supersonic aircrafts. It has a very peculiar property because of which it is used in these supersonic aircrafts. Okay, problem with supersonic aircraft is that the airfoil and the wing sections encounter a shock wave, which greatly reduces its performance. So this airfoil improves that performance. Okay, so there is one property by which it is improving the performance. Look it up and come back in the next class. Okay, supercritical airfoil. Okay, let's move on. Next question was the aspect ratio of an airfoil is. Airfoil, like we just discussed, is the cross section of a wing, right? What is aspect ratio? What is the formula for aspect ratio? AR is wingspan by chord. Is that true? Yes, answer is infinite. What was the formula for aspect ratio? Okay, write down B square by S, right? So what was B? B by C will be true only if it's a rectangular cross section, right? Rectangular span, I mean. Otherwise, it will be B square by S. Yes. So B is wingspan, S is the area, right? Wet surface area, right? So B square by S is the aspect ratio. Now, what is the span of an airfoil? B. What is the B span of an airfoil? What is it? They've asked you aspect ratio of an airfoil. So what is the span of an airfoil? What is the span of an airfoil? Of an airfoil, it will be infinite, right? So it is, so wing is a finite body. So airfoil, though we consider it to be the cross section, we assume it to be of infinite length, right? So that is why your aspect ratio will be infinite. Okay. Okay. So can you tell me how the lift curve slope will change with respect to change in airfoil, with respect to change in the span? So if I, one second. So if I have, if this is my lift curve slope of an airfoil, this is CL, this is alpha, and this is aspect ratio, say infinite. So infinite aspect ratio is airfoil. Now, if I have a wing of aspect ratio, say 10, how will the lift curve slope look? I believe this is one of your questions, I think, in one of your assignments, something similar. So I'm trying to help you to solve it. So if I reduce, so from aspect ratio infinite, I'm reducing it to 10, right? So how will your lift curve slope look? So I'm taking from an airfoil, I'm making a wing of aspect ratio 10, right? So how will your lift curve slope look? Okay, what happens when you make a wing of finite length? Wing area will increase lift. Okay, increase in wing area will increase lift. Okay, let's just look at this. Okay, so you have a wing of finite length, right? So initially it was just an airfoil that is of infinite length. Now, when you make it a finite length, you have a wing, right? So this whose cross section is the airfoil. You have a finite length. This is the fuselage. This is where it's attached to the fuselage, and this is your wing tip. Right? So this is your tip. So when there is an oncoming wind, so this is your V infinity. This is free stream velocity. When there is an oncoming wind, there is a flow below the wing surface. There is a flow above the wing surface, and both of them interact at the wing tip. When they interact at the wing tip, you have vortex generation there. So you have one velocity going from below and one velocity coming from above. And at that point, you have vortices being generated because of this intersection of the flow. Now, when these vortices are generated, what happens is the effective lift, effective angle of attack and effective lift reduces, right? So there's an increased drag production and there's a reduction in the lift. So what happens when you decrease the aspect ratio is that the lift reduces, right? So you have, this will be the aspect ratio 10. And when I reduce it further, it will reduce slope further. Aspect ratio 5, okay? So now just have a look at the vortex generation. So this is what I told you. So you can see these blue arrows, right? So the interaction of the flow above and below the wing lead to vortex generations, which then travel downstream of the wing. But that is not what we're looking at right now. Due to this vortex generation, the lift generation at the tip is reduced, which is why our lift curve slope reduced, because for the same angle of attack, your lift generation is less, okay, because there is an induced drag component. So vortex generation leads to reduction in lift and increase in drag component called induced drag, okay. The people from the aerospace background should be knowing this. There is an induced drag component due to this vortex generation, okay. So these figures are just representative of the vortices. Let's go to the next slide. Next question was, longitudinal stability of an airplane depends upon. Okay, now that you have gone through the week 1 contents, you should be able to answer this question. What is stability? Can you tell me what, not with respect to aircraft, just in general sense, what is stability?
Ma'am, it's like coming back to the original position after being disturbed.
Yes, correct. So initially, if it was at equilibrium, okay, so it means coming back, tendency to come back to the initial equilibrium. You're right. So when I say with respect to an aircraft, what will it be? For longitudinal stability, what will it be? Just extrapolate this idea of stability to an aircraft. Initial tendency to. So if your aircraft is flying at some angle of attack and there is a gust and it's deflected upwards, so there is a pitch up, nose up, right? So the tendency of the aircraft to come back to its equilibrium is the longitudinal stability. This is with respect to longitudinal dynamics, okay? So when it is pitched up, tendency of the aircraft to come back down is longitudinal stability. Now, which of these components do you think will contribute towards stability? Is it the tail arm, control surface area, type of winglets, or none of these? Do none of them contribute? Tail arm, yes, you're right. So we had in week 1, there was an equation of the tail contribution, which we'll be revising in a bit. So the tail arm is what contributes towards longitudinal stability. Why? Let's just have a look at this. So if this is your fuselage reference line and this is your wing, right? So there is a lift component here. So now it's flying at, say, suppose some equilibrium angle of attack. Okay, so now it's flying at equilibrium. Now, due to a gust, this fuselage reference line, the entire thing is lifted upwards. So what happens is that there is a delta alpha, right? So now if you want your aircraft to come back, so initial alpha 1 was alpha. The second alpha, the disturbed alpha, is alpha plus delta alpha. Now, if you want your aircraft to go back to alpha, what do you have to do? You have to reduce that angle of attack. So what should happen? The aircraft should pitch down. Now, how do you make it pitch down? if this is your CG, you need to have some force component here that will produce a moment, pitch down moment. Okay. So that is the tail, right? So tail is the structure that generates a lift such that you have a restoring moment. So you have a tail here, which generates the restoring lift that produces the restoring moment. So if the aircraft is subject to some disturbance, the tail will generate enough lift to produce a restoring moment to get the alpha back to the original alpha 1. All right. So tail is the structure that contributes towards stability. Okay. So from these three quantities, the tail arm is nothing but the distance between CG and this is the tail arm. Okay. So it's called LT. The distance between the CG and the aerodynamic center of the tail is the tail arm. Okay, so tail arm is the right answer. Okay, control surface area. Why doesn't a control surface area contribute towards stability? Can someone tell me? We will obviously look at the equations of tail contribution, but can someone just tell me why doesn't what is the control surface in this case? Elevator, yes. Why doesn't the control surface area contribute towards stability? Okay, we will get to this when we look at the larger area will create more moment. Okay. Okay, we'll get to this question when we look at the tail contribution equation, okay, in just a bit. So which of these terms is not associated with an airfoil? So before this, we'll just look at some airfoil nomenclature. Yeah, so this is a typical airfoil. So it has various structures. So it has a leading edge. This is your leading edge. This is your trailing edge, right? So this is trailing edge. Then you have a camber, and this green dashed line gives you the mean camber line, right? So it is an equidistant from the upper surface and the lower surface. Now over this entire cross section, the region of maximum thickness is this thickness, okay, T. So in our question, it says T by C, thickness to chord ratio. What is chord? Chord is the line that connects the leading edge and the trailing edge, the straight line that connects the leading edge and the trailing edge. How is it different from the mean camber line? How is the chord line different from the mean camber line? From this figure, just tell me. So the mean camber line is the one in green, chord line is the one in yellow. Okay, both of them connect leading edge to trailing edge. What is the difference?
Ma'am, mean camber line is dividing the both the parts in equal.
Okay. Okay. Yes, correct. So it is equidistant from both the upper surface and the lower surface. She's right. Okay. The chord line is just a straight line from the leading edge to the trailing edge. Okay. Represented by C. Chord length is C. Maximum thickness is T. Okay. Those are the terminologies that you need to be familiar with. So now let's go back to the question. Which of these terms is not associated with airfoil? T by C is the thickness to chord ratio. We know that that exists. Okay, so you have the maximum thickness T, you have chord C. Okay, next, spiral. Did you see any spiral there? No, this is fairly simple. So camber exists, chord exists. So the answer is spiral. Yes, Nandini, you're right. It's spiral. Okay, next. What is stability and control of an aircraft? So just don't look at the options initially. Just tell me stability. Yes, she had told me that it is tendency to return to equilibrium when subjected to disturbance. So I think the first two and the third have the same definition of stability. That is correct, right? So it has the same. Now let's look into control. Can someone tell me what is control? Don't look at the options. Just tell me what you understand by control. What do you understand by control? Stability is the inherent tendency of the aircraft to return to equilibrium position. Okay. What is control? Control, just from the term, what do you understand by control? It doesn't have to be with respect to aircraft. Just tell me what you understand by the word control. Direction of aircraft. Have a power to change things. Yes. So Yachit is right. It's have a power to change things. Okay. So now when I say control of aircraft, what I mean is to control its motion, to pitch up, yaw, roll. Okay. So we are controlling the aircraft. So we are producing an accelerated motion, right? It has nothing to do with equilibrium. We don't have to control the aircraft if it is at equilibrium. If we need to pitch it up, move it to a non-equilibrium position, then we need to accelerate the aircraft. So now look at the options and tell me what is aircraft control. The wordings are a little ambiguous, but just try to understand. So aircraft control is, the keywords are non-equilibrium position and accelerated motion. Okay, so it is, here it has non-equilibrium, accelerated motion. So this is the right answer. Okay, right? So the wordings are a bit ambiguous, I understand, but you get the idea of stability and control and how they are different. Okay, now let's begin with the first week 1 contents. So static stability, just like we had discussed before, stability is the initial tendency to go back to equilibrium. What is it for an aircraft? Again, we discussed this when the aircraft is flying. For longitudinal case, I'm just talking about the longitudinal case. If it is flying at some equilibrium, there is a gust of wind which pushes it up. The tendency of the aircraft to come back to its equilibrium is termed as stability, static stability, right? So if it is unstable, what will happen? It's flying here, there is a gust. What happens? If the aircraft is unstable, what will happen? It will continue deflecting up, right? Yes, it may stall, it will continue deflecting up. Now, since we have introduced the word stall, can you tell me what stall is? Stall. S-T-E-L-L. What is stall? Anyone, just what your understanding of the word stall? Max lift crossed, point at which lift suddenly falls. Okay. So now both of them are right? So let me just flow separation. Yes, all three are right in fact. So let me just draw this lift curve slope. Right? So this is CL, this is alpha. Now this is your point of maximum CL, right? So when the angle of attack reaches this angle, at this angle, which is referred to as alpha stall, it reaches the maximum lift generation capability. Any angle of attack beyond alpha stall, the lift drastically reduces. So both the first points are right. Why does it reduce? Now let's look into that. So if this is your airfoil. So initially this is your flow, right? Now I increase the angle of attack, something like this. What happens is it goes like this, right? So there is a flow separation here, and due to that flow separation, it is not producing as much lift as it should. So any angle beyond that alpha stall, it will not produce enough lift to sustain flight, and the aircraft will suddenly just drop, right? So all 3 points are right. Max lift crossed, point at which lift suddenly falls, and this is why it's happening. It's because of flow separation. Okay, it doesn't produce enough lift to sustain the flight. Okay, so this is the idea for static stability. Now I think sir would have taken an example of the ball in a bowl. So let's just go over that briefly. I think it's also part of your assignment. So let's just go over it. So there are 3 conditions. You have statically stable, neutrally stable, and statically unstable. Okay, so you have an inverted bowl. And if I have a ball here in the vessel, and if I push it to this point, it has an initial tendency. It has, in fact, it will come back to, it will swing and come back to its initial equilibrium point. So this is statically stable. Now, if I keep the same ball on a flat surface, okay. Now, if I move it, displace it to another location, will it come back to the original position? No, it will form a new equilibrium at the new point, right? So this was initial position. This is the new position. It will not come back to position 1. It will form a new stable equilibrium at the new position, okay? So this is called neutrally stable. Next condition is an inverted ball, and I keep a ball over it. If I displace it even slightly, it will just keep going further away from the equilibrium point and will show no tendency to come back, right? So this is unstable. Now this is static stability. Static stability is what tells you that it has an initial tendency to come back to equilibrium. What about dynamic stability? What does that bring into your mind? What does the word dynamic mean? Dynamic stability, just think about it.
Dynamic means moving.
Moving, yes. So when I say dynamic stability and with respect to time, yes, Nandini is right. Both of you are right when it's moving. So let me just take a graph and show you this. Suppose this is your equilibrium point. Okay, so this horizontal line is your equilibrium point, and I deflect it to some, I just push it, I disturb it to some position, and over a period of time, if it decays and tries to come back to its equilibrium, it is dynamically stable. Now, same thing, if I had disturbed it and it continues to deviate away, it is unstable, right? So this is the difference between static and dynamic. Dynamic is over a period of time, will it come back to its equilibrium or will it go away from the equilibrium? Static is just the initial tendency that it shows. Okay, so this is the difference. So beginning of this course, we will be dealing with static stability and we'll slowly go on to dynamic stability. Okay, so yeah. Now, next concept that we dealt with was aerodynamic center, right? So when you consider an airfoil, let me just draw this. So if it's an airfoil, when we study aerodynamics, what we see is that the lift and drag. So what are the aerodynamic forces? Lift and drag, right? So lift and drag are presumed to act at a point called center of pressure, right? So you have pressure being generated here, something like this. So you have some profile like this, and you have this is negative pressure, and this is positive pressure, which is why your airfoil produces the lift, correct? Now, it is presumed these forces, lift and drag, are presumed to act at a point called center of pressure, right? Now, what happens with the center of pressure is that it keeps changing with angle of attack. So when the same airfoil, if I were to keep it a different angle of attack, this pressure profile will change, right? So it will be something like this. So the center of pressure moves ahead. Center of pressure will be somewhere here. It was initially here, it moved here. So with change in angle of attack, the center of pressure keeps changing. It becomes very difficult to analyze the moment and the forces when the point of reference keeps changing. So we came about this point called aerodynamic center. What is aerodynamic center? It is a point that is independent of angle of attack. So aerodynamic center is same point at which the moment remains same throughout the flight duration. No matter how much the angle of attack changes, the moment at the aerodynamic center is the same. Okay, so it becomes very convenient to do your analysis when the point of reference is fixed. What happens now is that, so let's take another, so this was center of pressure, and suppose your aerodynamic center is somewhere here. So our lift and drag are acting at center of pressure, but we wish to do our analysis at aerodynamic center because it is easier, right? So when I transfer the forces to a different point, the forces get transferred. So my lift and drag are now here, but together with that, what comes? A moment is coming into picture, right? So when I move the forces from center of pressure to aerodynamic center, it comes with a moment. So in this case, the drag will not produce any moment. Lift will produce one pitch down moment, nose down, right? So it is in this direction. Nose down moment is produced. So that I can write it as M at AC, right? So when I move the forces from center of pressure to aerodynamic center, at the aerodynamic center, you have lift, you have drag, and you also have a moment, MAC, okay? Okay. Now, if it is a symmetric airfoil, what do you think will be the moment AC, MAC for a symmetric airfoil? What will it be? Think about it. Just think about it. Center of pressure and aerodynamic center. So when I transfer the forces from from center of pressure to aerodynamic center, it comes with a moment, right? Because there is a distance between center of pressure and aerodynamic center, which is what we refer to as MAC. That is moment at aerodynamic center. Now for a symmetric airfoil, what will it be? Just take a guess. 0. Yes, Sarthak is right. 0. Why? Can you tell me why it is 0? So what he says is MAC for symmetric airfoil is 0. Why is it? Because of symmetry. Yes, symmetric airfoil is symmetry, but what is it that makes that MAC go to 0? Why do we have an MAC? Because you're transferring the forces from CP to AC. So what is different for a symmetric airfoil? Why is it 0? Will act from both sides. No. For a symmetric airfoil, your center of pressure and aerodynamic center are the same point. Okay. So there is no distance between AC and CP. Hence, it will not have a moment component. Okay. Okay. Now, think about for a cambered airfoil. Will the MAC for cambered airfoil, will it be less than 0 or greater than 0 for a cambered airfoil?
Less than 0.
Less than 0. Correct. Correct. It's just like the image here. So when I transfer the lift and the drag to AC, it gives you a nose down. And by convention, I think I should have written that. Okay, so convention is nose down is negative. Nose up is positive. This is the longitudinal motion convention. Okay, so pitch up or nose up is positive. Pitch down, nose down is negative. Okay, so that is your convention. So for a cambered airfoil, it produces a pitch down. So it produces a pitch down moment. So the moment that comes when I transfer the forces is pitch down. So it is negative. MAC for an airfoil, for a cambered airfoil is negative. Okay. So this is just a depiction of how the center of pressure keeps changing with respect to change in angle of attack. Initially, you can see that it's at this point. And when I reduce the angle of attack to -8 degrees, the center of pressure moves back. When I increase the angle of attack to 10, the center of pressure moves ahead. So the analysis becomes extremely inconvenient because your point of reference keeps changing, which is why we came up with the aerodynamic center. Okay. Now another concept that was introduced is trim. Trim is something like an equilibrium. Okay. So the sum of the forces and moments are 0. So trim is the point where all your forces, summation of all your forces and moments are 0. Okay. So that is just a concept. Then, oh yes, now I've put the pitching moment convention here. Nose up is positive. We had just discussed this. Nose up is positive, nose down is negative. Pitch up is positive, pitch down is negative. Okay. Now, this is the equation for pitching moment coefficient, right? So it's Cm is Cm naught plus dCm by d alpha into alpha. So it is a straight line, right? So we are assuming it to be a straight line variation with the intercept as Cm naught and slope as dCm upon d alpha. Now for static stability, we require the slope to be negative. The sole condition for static stability is that dCm by d alpha, that is dCm by d alpha, or we refer to it as Cm alpha, should be less than 0. This is the condition for static stability. Another one condition that we have mentioned, that Sir has also mentioned in the lectures, is that Cm naught should be greater than 0. Okay, so now when I look at the curve, we know that the CMAC, Cm alpha should be negative, and we know that Cm naught should be positive. Okay, so I'm just drawing for a typical aircraft. How will it look? This is your line. So this is Cm, this is alpha, this is Cm naught, and you have a negative slope. So this is a statically stable typical aircraft. Now, if I have Cm naught negative, how will the curve look first of all? Can someone tell me? Here Cm naught is positive. If I have to make Cm naught negative, how will the curve be shifted?
Mirror image बन जाएगी y-axis पर.
Yes, so I just drag it down, right? So it will just be something like this. Correct? So now your Cm naught is negative. What happens here is that we just discussed trim. Trim is that when summation of all forces, summation of all moments is 0. So in this graph, trim is when Cm, pitching moment, is 0. So for the first case, let's take this as case A and this as case B. Case A, your trim is here. It's trimming at a positive angle of attack. For case B, it is trimming at this point, which is a negative angle of attack. So we prefer our aircraft to be trimmed at a positive angle of attack, 0 or positive, but it's preferred to be at a positive angle of attack. So the condition to ensure that your aircraft is trimmed at a positive angle of attack is that your Cm naught should be 0. Okay. So this Cm naught is 0 is not a condition for static stability, is not a condition for any stability. You need to keep that in mind. The only condition for longitudinal stability is that Cm alpha should be 0, less than 0, right? This condition, Cm naught greater than 0, is only to trim your aircraft at a positive angle of attack. Okay. Now I've put up this question that asks how to ensure Cm naught is greater than 0. Now let's get back to our initial question of reflex airfoil. Where was that? Yes. So this is our reflex airfoil. This one is reflex. Now, can you try, with the knowledge that you have now, can you try to tell me why do we have reflex airfoil? So for symmetric airfoil, this is symmetric. This is cambered. Your Cm naught or CMAC is 0, right? Because center of pressure and aerodynamic center are the same point. For symmetric airfoil, the Cm, pitching moment that comes because of transfer of forces, is 0. For cambered airfoil, your CMAC is less than 0. So for reflex airfoil, what will change? For cambered airfoil, this is your CP, this is your AC. For reflex airfoil, how will it look? Just try to put everything together. Just try. So symmetric airfoil, CMAC or Cm naught in this case is 0. Cambered airfoil, it's less than 0. That means, so cambered cannot be trimmed at positive alpha. So if I have to trim the aircraft at positive alpha, what do I have to do? In this case, there are no other structures. It has only wing, right? So it was just a flying wing configuration. Will it be greater than 0? So for reflex airfoil, depending on the curvature at the trailing edge, your CMAC can either be equal to 0 or greater than 0. Okay. So I had mentioned that we prefer CMAC to be greater than 0 so that we can trim the aircraft at a positive angle of attack. But even 0 is fine. But you do not generally prefer to trim your aircraft at negative angles of attack, which is why we don't take a cambered airfoil for just wing configuration. Okay. So the trailing edge curvature up ensures that the CP moves towards aerodynamic center. So ideal case for reflex is AC and CP at the same place, or Cp can even move ahead, okay, producing the CMAC greater than 0. Okay, depending on the curvature at the trailing edge, Cp can either be at AC or ahead of AC, giving you CMAC 0 or greater than 0. So this is for Cp equal to AC. This is for, what do I say, Cp ahead of AC. Okay. So that is why we brought into picture the reflex airfoil. That is why it was designed. Let's get back to our slides. Okay. So can you think of any other way we can ensure CM not to be greater than 0? So for if it is just a wing, there's nothing you can do except for the reflex airfoil. Any other way to make CM not greater than 0? You have all gone through week 1 contents, right? So I'm just going over the topics. So from whatever you've learned in week 1, can you try to tell me another way we can make CM not greater? CM not is this intercept, right? So it's this point. How can we ensure it to be greater than 0? One way is reflex airfoil, right? Another way, if I have other structures other than wing, what can I do to make CM not positive?
We can give big wing setting angle.
Wing setting angle, yes, wing setting angle. But you considering that there is a tail, right?
Yes, ma'am.
Yes, correct. So now let's go ahead into the wing contribution and tail contribution towards CM. So this equation, I'm pretty sure you know how to derive it, but I'll just write it down. So if you have just a wing, so your fuselage reference line, you have a wing, and this is your CG, this is your AC. So your lift is here, drag is here, and you have some moment and AC. So now let's take the forces at the CG. So moments at the CG. So you have mcg equals, can you just give me the equation, equilibrium equation? So it will be lift. Okay, before that I need to mention the, 1 second. So this was XAC and this distance is XCG. This is okay. Now let's take the moments at CG. Moment at CG is lift into XCG minus XAC. Now drag will not produce any moment because we've considered CG to be on the fuselage reference line. Then you have plus MAC. Okay, so now you take a non-dimensionalize it by taking the coefficient of moment. So you have CMCG. So what was CL? What is the equation for CL? Okay, so lift is half rho v square SCL. So similarly, what is pitching moment? Half rho v square. Am I audible? Are you with me?
Yes, ma'am.
Okay, so lift is half rho v square SCL. Now for pitching moment, M is half rho v square. So you know that there will be a CM here, but what else? Are you familiar with this equation?
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, so similarly, try to tell me for pitching moment, half rho v square. It will be S and C. Exactly, Harshal is right. So half rho v square SCCM. Okay, So now when I non-dimensionalize this equation, I just divide throughout by half rho v square SC. Okay, then I get the CMCG. Okay, so divide on LHS and RHS by half rho v square SC. And then what will I get here? I will get CL by C X. So it will be XCG minus XAC plus CMAC. Now, if I expand CL, CL is what? CL is CL naught plus CL alpha into alpha. Right. So if I expand this, it will be CL naught X bar CG minus X bar AC plus CL alpha X bar CG minus X bar AC into alpha plus CMAC. So this is the equation that I've written here, right? So this is that equation. That is how it's derived. Now, if you have a tail, if you have one tail here, you take its lift and its drag. So you will be lifted tail, dragged tail, and you will have another distance XAC tail. Similarly, you add on the components. So here you will have one minus L into XAC tail minus XCG, right? And then you derive it so on and so forth to get your wing contribution, tail contribution. So this is your wing contribution and this is your tail contribution, wing, tail. Okay. So let's just go to the next slide. Yeah. So this is your wing contribution. And this is your tail contribution. Okay. So now each of those contribute towards CM naught, CM alpha. Our main equation was CM is CM naught plus CM alpha into alpha. So now in this wing contribution, what is CM naught? This is wing, this is tail. In the wing contribution, what is CM naught? What is the wing contribution towards CM naught? What is the wing contribution towards CM naught? Just equate these two equations. So the terms dependent on alpha, terms independent of alpha. Just look at that. Okay, in this W equation, can you tell me what terms do not depend on alpha wing? This alpha wing, alpha W, which term does not depend? Yes.
First two terms.
Yes, first two terms, correct. So this entire thing is the CM naught contribution of wing. And this one is the CM alpha contribution of wing. Similarly, for tail, we have this entire thing is the CM naught contribution of tail. And this entire thing is the CM alpha contribution of the tail. Okay. So just keep this in mind. There may be a few questions that ask you to find out wing contribution of CM naught, tail contribution of CM alpha. So just keep this in mind. And if you do not remember this equation, we just saw how you can derive it. Just start with the basics and you can derive it. It is simple. Okay. So now our initial question was how to make CM naught greater than 0. So one way was to use a reflex airfoil. What does a reflex airfoil do? This CM alpha itself will be positive. Okay. What is the other way to make CM naught positive? Next term is this. Is there any way to make this positive? No. Right? Because your CG will always be after your AC. So this quantity will always be negative. Correct? Correct? For a stable aircraft, that quantity, yes, so it will always be negative. So this term cannot contribute towards positive Cm naught. This term will get you reflex airfoil, this term cannot contribute. Next, we move on to the next and the third component of Cm naught, which is this. To make that term positive, what can you do? You can make wing setting angle greater than tail setting angle. You can make tail setting angle less than 0. All of these are the ways to ensure that the Cm naught is positive. Somebody had mentioned previously, I think Yachit had told that wing setting angle should be increased. Yes, that is one way to make your Cm naught positive. Why do we need Cm naught positive again? I had asked this question, we had discussed it. Why do we need Cm naught positive?
Trim. करने के लिए.
Yes, to trim the aircraft at positive angle of attack. It is not related to stability in any way. Okay. For stability, Cm alpha should be negative. To trim the aircraft at positive angle of attack, Cm naught should be positive, but it doesn't deal with stability. Okay. Now, what is neutral point? We have seen aerodynamic center. Aerodynamic center is the location at which the pitching moment is independent of angle of attack. Now, neutral point is something. So aerodynamic center was for a wing. Neutral point is for an entire aircraft with all structures, wing, tail, everything. So neutral point is like neutral point of an aircraft is like the aerodynamic center of a wing. Okay, let me just write that down. AC of wing is akin to neutral point of aircraft. Okay, so these are the same similar concepts. So it says CG location at which Cm alpha is 0. So when it doesn't change with respect to angle of attack, that is your neutral point. Now, the equation for static margin. What is static margin?
Ma'am, the distance between XCG and
Distance between?
Neutral point and C.
Yes, neutral point and CG. So what does it measure? What does it tell you? It's given here that it's distance between neutral point and CG. So if I say static margin is greater, what does it physically tell you? What is its significance?
Neutral point is far than CG. If it's
Okay, but what is the effect on the stability or the control of the aircraft? So static margin is a quantitative way to measure your stability. So greater the static margin, greater is your stability. Correct? So if your neutral point is far away from CG, the aircraft is that much more stable because it will produce that much restoring moment. Correct? Because your moment arm is large. Yes? So if your static margin is greater, your aircraft is more stable. So it's like a measure of stability. It's a value to tell you how stable your aircraft is. Okay. It is also the negative slope of the dCm upon Cm versus Cl or Cm versus alpha graph. It is the negative slope. Okay. So that is your static margin. Now let's look over a few questions based on these concepts. So aerodynamic forces acting on the aircraft depends on relative ground speed, wind speed, relative airspeed, or none of these. What are the aerodynamic forces? What are the aerodynamic forces? We just discussed this.
drag, lift.
Yes, lift and drag. So do they depend on relative ground speed, wind speed, relative airspeed? What is it? So that formula that we just wrote, lift is, what was the formula? In the previous slide we wrote it, where was it? Yes, this formula.
CL half rho V square.
Half rho V square SCL. It depends on this velocity. What velocity is this? It is the relative airspeed, right? So it is your free stream
Yes, sir.
velocity. So either the aircraft is moving with respect to the air or the oncoming air. However you see it, it's the relative airspeed. Okay. So this is the answer. Somebody has said lift, drag, thrust, and weight. How can you tell me how thrust is an aerodynamic force? Does it depend on the relative airspeed? So thrust is a propulsive force, right? So your propulsion system produces the thrust, either the propeller or the jet engine or whatever produces the thrust, right? So thrust is a propulsive force, and weight is definitely not an aerodynamic force. It is the gravitational component, right? Gravitational force. So you have three main types of forces: propulsive, aerodynamic, and gravitational. Gravitational is the weight, propulsive is the thrust, and aerodynamic is the lift and drag. Okay. I hope that settles that. Okay. Let me know if you have any question. Okay, next question. Yeah, so lift and other aerodynamic forces are generated by the motion of an aircraft through air. Okay. Which one is correct about aerodynamic center of an aircraft? Aerodynamic center does not depend on location of center of gravity. It depends on location of center of gravity, depends on neutral point, none of these. What is aerodynamic center? Can somebody just give me a definition? We just discussed this.
Where ma'am, net pitching moment is 0.
Yes. Okay. Where pitching moment is independent of angle of attack.
Sorry, yes ma'am.
Where pitching moment is 0, what is that point called? So aerodynamic center is where CM is independent of alpha. What you had said is pitching moment is 0. What is that point called?
Maybe neutral point.
No. Just think about it. Center of pressure. No. Center of pressure is where your lift, drag, all of them actually act. Okay. And we transfer them to your aerodynamic center for ease of analysis. Okay, so let me just clarify this once and for all. Center of pressure is where lift and drag act. Okay. Aerodynamic center is where CM is independent of alpha. So aerodynamic center is also where you transfer your lift and drag. Transfer, lift and drag. Okay. Next one point is where CM naught is 0, or where the moments are 0, where the forces are 0. What is that point? We just discussed this. Is it? Yes. Where the net forces and moments are 0. Right? So it's called trim. So this would be trim. Okay. Coming back to the question, which one is correct about aerodynamic center? Aerodynamic center is the point where CM is independent of angle of attack. Okay. Now look at the options and tell me. That is the only way to define aerodynamic center. Okay, now just look at the options and tell me. It does not depend on location of center of gravity, depends on location of center of gravity, depends on neutral point. Does it depend on the location of center of gravity? Does the aerodynamic center depend on location of center of gravity? No, correct. So that is the right. What is center of gravity? That's another point. CG. Another one is neutral point. Let's discuss all of these. What is CG? Very simple. What is CG? Net weight x. Yes. Weight x. What is neutral point? Okay. Neutral point is just like the definition for aerodynamic center. These are the same thing. Aerodynamic center is for a wing. Neutral point is for an aircraft. They are the same definition. CM is independent. Alpha. Now for stability, should the neutral point, let's just take wing. Okay, so should the aerodynamic center, okay, let me see. AC, CG. Another one is CG, AC. Which is stable? This is configuration 1. This is configuration 2. Which is stable?
Second one, ma'am.
Yes, second one.
Yes, ma'am.
Yes. So CG has to be ahead of aerodynamic center. Okay. Then now let's look at neutral point. So you have neutral point, CG, CG. Again, you have 4. Amongst 3 and 4, which is stable?
Third one, ma'am.
Third one?
Static margin में पढ़ा था ना. Static margin should be positive.
So what was static margin?
XCG. ठीक है, ma'am.
Okay, let me just draw this. So if I take some reference point, so this is XCG, this is XNP. Your static margin is XNP minus XCG. If static margin has to be positive, third or fourth, which is the correct option? Fourth, yes. Right, so the fourth one is stable, statically stable. The static margin is positive for the fourth case. So one way that I use to remember this very simply is just remember CAN. Okay, so CG has to be ahead of both aerodynamic center and neutral point. So that is how I remember it. You can use anyway, but this is how I remember it. CG has to be ahead of aerodynamic center. If it is just wing, CG has to be ahead of aerodynamic center. If it is the entire aircraft, CG has to be ahead of neutral point. Okay, but CG has to be ahead. That is when your static margin is positive. All right. Okay. So this is just something that I used to remember. A wing is made of symmetric airfoil. The pitching moment coefficient at 0 degree angle of attack will be. What will it be? Read the question carefully. Symmetric airfoil, pitching moment coefficient. What is the notation for pitching moment coefficient? What is pitching moment coefficient? What do we use it? We've been deriving these equations. What is the notation? CM, right? Now, what is pitching moment coefficient at 0 degree angle of attack? How do you
CM
denote?
naught.
CM naught. Correct. CM naught. So for symmetrical airfoil, CM naught should be positive, 0, negative, or none of these.
0.
0. Yes. For a cambered airfoil?
Negative.
And for reflex?
Positive.
Yes. It can be positive or 0. Okay, so it won't be negative, that's all. Okay. Okay. So this is the right answer. Next question. Yeah, so I just noted down the point. Symmetric airfoil, CP at the center of pressure and aerodynamic center are the same for the symmetric airfoil, which is why you don't have a moment at the AC. Then lift side. Okay, so these are stuff that we know. Okay. Positively cambered airfoil produces what? Considering leading edge up, that is pitch up is positive. Okay, that is your notation. So nose up, pitch up, they're all positive. Okay. Now positively cambered airfoil produces positive pitching moment, negative pitching moment about CP, 0 pitching moment about AC. Read the options carefully and tell me the answer. Can you tell me? Positively cambered airfoil produces positive pitching moment about AC, negative pitching moment about AC, negative pitching moment about CP, and zero pitching moment about AC. Which is the right? Read both the parts carefully. What is the pitching moment about CP? For any airfoil, what is the pitching moment about the center of pressure? Cm at Cp, what will it be? Yes, at Cp you will have zero. Okay, because your forces are acting at your Cp. So there is no moment there. It's only because you transfer the forces to the aerodynamic center that you have a moment. Okay. So obviously this is wrong. Okay. Now look at the other three options. Positively cambered airfoil, will it have positive pitching moment about AC, negative pitching moment about AC, or zero pitching moment about AC? There will be no pitching moment at center of pressure for any airfoil because your forces are acting at center of pressure. Option D. Option D. Can you tell me why? So Srini says it is option D. Can you tell me why? Can you just try justifying your answer? Just try. Just put it up on the chat box if you find it hard to speak. So now let's just go over this question again. Positively cambered airfoil. Let's just draw that. Now, how do you find out pitching moment? You take CP and AC. Now, if I am telling you that this is AC for a positively cambered airfoil, where will CP be? After or ahead of AC? We just discussed this. Okay, the previous question itself. So for a symmetric airfoil, your Cm naught was 0, right? For cambered airfoil, okay, now can you try to answer this? For this airfoil, this is a positively cambered airfoil. If I'm telling you that this point is AC, then CP, the center of pressure, will it be behind it or ahead of it? We had just discussed this. Where is it? Yes, the first slide, very first slide, we had discussed this. So if this is a cambered airfoil, AC is here, CP is ahead or behind AC?
Behind.
Behind. What happens? Let's go back to our slide. When I transfer the lift to AC, it comes with a moment. It comes with nose down or nose up moment. When I transfer this lift to AC, it comes with clockwise or anti-clockwise moment?
Anti-clockwise.
Anti-clockwise, which in this case is nose down, right? So it comes like this. That is nose down. Nose down is positive or negative?
Negative.
Negative.
So your answer is negative. It's the same question as this question. It's just formed or phrased in a different manner. Okay. Do not get confused. It's the same question. They're asking you for the same thing. Positively cambered airfoil produces negative pitching moment about aerodynamic center. That means your CM naught or CMAC is negative for cambered. CM naught equals CMAC equals 0 for symmetric. Okay, so these are just two ways in which the same question is being asked. Do not get confused. Okay, let's go to the next question. A positive tail incidence angle setting as compared to zero tail incidence angle setting will result in. Now, before we go ahead with this, what is the notation for tail incidence angle setting? From our equations, what was the notation? When I say notation, I mean what alphabets or what letters do you use to depict tail incidence angle? Tail setting angle, tail incidence angle setting. Okay, in this equation, can you look at the tail? Okay, I think we have to go over this. What is VH? This term VH, what is VH?
Horizontal tail.
Horizontal tail, what is it? VH is horizontal tail volume ratio, right? And what is the formula? So VH is equal to ST upon S C, sorry, LT upon C, where ST is the tail area, S is the wing area, LT is the momentum. Momentum is what? What is momentum? Tail momentum is what? LT is XAC tail minus XCG. Okay, this is your tail momentum. And C is the mean chord of the wing. Okay, next. What is this eta? What is eta? What is eta? What is that eta? Is V infinity dash square by V infinity square. What is V infinity? It's the free stream velocity seen at the wing. Now at the tail, due to this vortex generation, there is a reduction in the velocity. Okay, so it will not be the same velocity, which is what is this ratio. Okay, so it's the tail efficiency factor. CL alpha tail. What is that? What is this? What is CL alpha tail? How do you categorize that? How do you say? It's the lift curve slope of the tail, right? Correct me if I'm wrong. Just try to get an empty slide. So this is your lift curve slope, right? So if I write the equation for this in the linear section, you have CL equals CL naught plus CL alpha into alpha. Okay, so this is your intercept. This is CL naught. This slope is CL alpha. CL alpha is dCl upon d alpha. Okay, lift curve slope. So that is what here you have the lift curve slope of the tail. Now what is IW? What is IW? One of you had in fact told me when I asked you what is CM not greater than 0, you had told me this thing. What is IW? Am I audible?
Yes, ma'am.
Okay. Okay. Can anyone try to tell me what is IW? No? IW is the wing setting angle. What is wing setting angle? From the word, can you try to tell me what wing setting angle is? Okay. So let me draw this. This is your fuselage reference line. Now, if your wing is initially fixed on the aircraft at an angle, this is your I wing. Okay. Aircraft is not flying anything, it's at the ground level. If your wing is fixed on the fuselage reference line at an angle, that is called wing setting angle. Similarly, IT is tail setting angle. Yes, is that clear? Okay. Now, what is this epsilon naught? Let me try to get an empty slide. 1 second. Why didn't you tell me that you were not familiar with these terms? I thought it was this derivation done in week 1? It was done, right? Sir had done this. Okay, so what I want all of you to do is this week go and try to do the derivation for these two equations, this wing and tail. Wing, I think we have done. This is the wing derivation. Do the similar thing for tail. Look at the videos, try doing it. And we will do this derivation in the next class, okay? Just go through it once yourself. Look at all of those terms. If there is any notation that you're not familiar with, we will deal with it in the next class. So I'll just go over this epsilon. So epsilon, let me just erase these. So anywhere you have any doubt when I'm going over the equation, just stop me and ask me, okay? Okay, let me just tell you what epsilon is. Epsilon is again linearized, epsilon naught plus dou epsilon by dou alpha into alpha. Epsilon is the downwash angle. What is downwash? We had seen that there is this vortex generation at the wing tips, right? So these vortices, yes. So these vortex generation, they're generated here at the wing tips. Now they travel backwards, right? So these vortices travel backwards towards the tail. When it reaches the tail, what happens is that the velocity that the wing sees is not the same velocity that the tail sees. Okay, because of these vortices, there is a difference in the velocity. Similarly, there's a difference in the angle of attack. Everything changes at the tail by a margin. Okay, so the difference in the angle of attack seen at the wing and the tail is this downwash angle, epsilon. All right. Yes. So that epsilon is represented in terms of alpha using this equation. Now, when we use this epsilon in this derivation, you will find that it appears in two different components. So how is it featuring into the final equation? So you have angle of attack at the wing. So in this previous derivation, we saw that angle of attack of the wing is what we are seeing, right? Now, when we take tail, you will have angle of attack at tail. Okay. Angle of attack at tail is nothing but wing setting angle minus wing setting angle plus tail setting angle and minus epsilon. Okay, when you do this derivation, just look at this. This will be the formula for angle of attack at tail, where I wing is wing setting angle, IT is tail setting angle, epsilon is the downwash angle. What is downwash angle? Due to the vortex generation at the wing, there is a reduction in the angle of attack at the tail. Okay, angle of attack seen by wing is not the same angle of attack seen at the tail. Okay, so there is a reduction in this angle of attack. That reduction is this epsilon. Okay, downwash angle. Right, epsilon is downwash. Is that clear? Is there any confusion with this term? We will do this derivation in the next class. Let's just go through it and come. But as of now, is there any confusion with the terminologies? So VH is the horizontal tail volume ratio. Eta is the tail efficiency factor. CL alpha T is the lift curve slope of the tail. IW wing setting angle. Epsilon downwash angle. IT tail setting angle. Okay. Any other term that you are not familiar with? Okay. Do this derivation and please do the derivation before you come to the next class. We will do it in the class, but it will be easy for you to follow. Okay. It's in the same manner. So first you write down the moment at the CG. We've done this for wing. Do it for the tail. This is the tail component. Okay. So the only difference here will be you will have this alpha, that is angle of attack at the tail, which is nothing but this one. I will be uploading these slides. So this should be fairly simple, but we will do the derivation in next class as well. Coming back to our question. Yes, a positive tail incidence angle setting as compared to zero tail incidence angle setting will result in. So I'll just write down the equation. Yeah. So this is the equation and tail setting angle is here. So just tell me if that is positive and zero, what will the difference be in the stability? So this is Cm naught of tail. This is Cm alpha of tail. Does Cm naught contribute towards stability? What is the condition for stability? Only condition. What is the only condition for stability? We had discussed that there is only one condition for longitudinal static stability. What is the condition? Yes, Cm naught is only for trim. So what is the condition for stability? CAN, yes. So that means that Cm alpha should be less than 0, right? For stability, for static stability, Cm alpha should be less than 0. This was the condition that we had discussed. This one. So this is the only condition necessary for static stability. It should regain equilibrium. That means that Cm alpha should be less than 0. Right? So the only term that is necessary for equilibrium is this Cm alpha should be less than 0. Now is this tail setting angle, IT, is it coming anywhere in Cm alpha? What is CAN? It's just a mnemonic that I had come up with. So CAN, CG should be ahead of both aerodynamic center and neutral point. There is no meaning for CAN. This is just something that I used to remember. You don't have to follow it. I just thought it would be easier. So forget about that. Now just tell me that is this tail incidence angle, which is IT, is it coming anywhere in your Cm alpha contributions? No. So tail incidence angle does not contribute towards stability. So a positive tail incidence angle, negative tail incidence angle will not give you more or less stability. It will remain the same. Okay. It only changes Cm naught. Cm naught is for, like it was mentioned here, like Yachit had said, it's only for trim. Okay, Cm naught is only for trim. So this tail setting angle, wing setting angle, epsilon naught, all of them will contribute only towards this trim condition, not towards stability. What contributes towards stability? VH, eta, CL alpha tail, dou epsilon by dou alpha. These things contribute towards stability. So the right answer here for this question is same static stability. Changing the tail setting angle does not change the stability, does not affect stability in any way. Okay. Okay. So for a static stability levels, slope is Cm versus Cl is minus 0.12. Okay. So let me just write down dCm by dCl is minus 0.12. And the pitching moment coefficient at zero lift is equal to 0.055. So Cm naught is 0.055. In this case, Cm naught is positive, so it is possible to trim the aircraft at a positive angle of attack. All right. What is the trim lift coefficient? Okay. How do we do this? Any idea how do we start doing this? How do we start doing this? Just take the basic equation for pitching moment. What is the basic equation for pitching moment? The straight line equation. What is the equation? So it is Cm is Cm naught plus Cm alpha into alpha, correct? Your straight line equation, Cm versus alpha. Okay, so now let's just expand this. So this is Cm naught plus dCm by d alpha into alpha. We don't have dCm upon d alpha, we have dCm upon dCl. So let's just modify this so that we get that term. You have Cm naught plus dCm by dCl into dCl by d alpha into alpha. Then what do you get? Cm naught plus dCm by dCl to Cl alpha into alpha. Cl alpha into alpha is what? Is Cl. Correct? So Cl alpha into alpha. This dCm by dCl into Cl alpha is just Cl. All right. So now we have this. They've asked you to find out Cl at trim. At trim, what happens? At trim, your Cm equal to 0. So your LHS is 0. So what do you do? 0 equals Cm naught plus dCm by dCl into Cl. Now plug in the values and tell me what is Cl at trim. What is Cl? Five, 0.12. What is this value? Just it's a simple division. Just tell me the value. Use your calculators, your phone calculators. Tell me the value. Am I audible? 0.4583. Okay, so I haven't calculated it. I'm hoping that's the right answer. It's a simple division. Is this easy to follow? Is there any question? So I started with the straight line equation and modified it to include the terms that we have. All right. Okay. Next question. Yeah. The primary control for yawing motion of an aircraft is
Rudder.
rudder. Yes. What is aileron? What does aileron control? What motion?
Aileron for roll motion.
Elevator.
Elevator for pitch up and pitch down, ma'am.
Yes. Okay. And throttle. Is it a control surface?
Ma'am, no, ma'am.
No. Yes. Okay. So this is the image. So the three axes. Let's just go over it briefly. The roll axis in the direction of the nose of the fuselage. Yaw axis downward towards the underbelly, and pitch axis completes your triad. Okay. So any motion above the pitch axis is the pitching motion, rolling motion, yawing motion. How do we control the pitching motion? It's through elevators. Okay, so these are the elevators. Yawing motion controlled through deflection of rudder. This is the rudder. This is the elevator. And which is the aileron? On the wing. Right? So aileron controls the rolling motion. Deflecting the ailerons left, downward, upward, rolls the aircraft right and left. All right? Now, also this is just something to show you how the elevator works. Deflecting the elevator downward creates an additional delta L, which pushes it in this direction. If you deflect the elevator up, produces a lift downward and will produce a nose-up motion. Is that clear? So if I deflect the elevator down, will it be nose-up or nose-down? Elevator down. Yes, nose down. Elevator down, pitch down. Okay. So this is one thing that I wanted to bring up in this class. So what it was is, what is the difference between the yaw angle and side slip angle? Yaw angle, we just saw what is yawing motion. It is, so if your aircraft is moving in this direction, this would be yaw, and the angle is side. Okay. How is it different from the side slip angle? There is a difference. Can you tell me how? So yaw, you understood, right? This side is understood. So if your aircraft is initially going in forward direction and then you turn it, so that angle from the reference plane is yaw. What is side slip angle? It is similar, but it is not the same thing. What is the difference? Okay, what is angle of attack? Drifting of the plane. Okay, okay, and that is not very clear. What is angle of attack? Alpha. What is alpha? Can you tell me what alpha is? Okay, I feel like I should have begun with this question. What is alpha? Angle of attack. Can someone give me the definition of alpha?
Angle between a relative wind and plane. Flight path.
Okay, relative wind and the chord line of the wing. Okay, so that is the proper definition. But yes, flight, not flight path. It is the angle between alpha. Is the angle between relative wind, that is V infinity, and chord line. Okay, so beta is a similar quantity. Beta is the angle between. So initially, when we see for our regular calculations, what we see is that V infinity happens in this direction. Now, if there is a gust and the V infinity is shifted, if V infinity is shifted in this direction, the angle between the fuselage reference line and the relative velocity is beta. Okay, we are not turning the aircraft. Your velocity is moving. Okay, turning the aircraft would be yaw. We want to turn it, so it is yaw. But when the velocity, oncoming velocity shifts from this direction to this direction, it is side slip. All right. So it was initially perpendicular, and because of some wind or some gust, it has shifted towards one side, which is why it is forming an angle with the fuselage reference line. That is side slip. But if you're turning your aircraft, that is yaw. Do you see the difference? Just think about it, read about it a little more, and then come back to the next class. The difference between yaw angle and side slip. Okay. Just go through it before the next class. This is a common confusion that is there for every course. Okay. Now, stalls normally occur on what part of the wing first? Wing tip, wing root, wing midsection, or at no point? What was stall? 3 points. People had mentioned 3 points. What was stall?
Ma'am, where maximum and
Maximum?
ma'am, where the lift is 0.
Where the lift suddenly starts dropping. Yes. Where the lift is 0, initially also the lift is 0. So we can't say that. Okay, so where it crosses the maximum lift and then starts dropping suddenly. Okay, so that is when it stalls, when it doesn't produce enough lift to keep the aircraft flying. So does it happen first at the wing tip or the wing roots?
Wingtip.
Can you tell me why?
Yep.
Okay, at the wing tips, we have vortex generations, like I told you. Because of these vortex generations, the angle of attack, the effective angle of attack at the wing tip is reduced. There is a drag component there, so the angle of attack at the wing tip is reduced. Okay, so even if your wing root is at stall, if you take the same angle at the tip, it becomes reduced. So your root has a tendency to stall first, which is why we generally wings have a twist. Okay, I don't think this was dealt with in the class. This is just some questions just to pick your interest. Okay, so the roots stall first. So if there was no vortex generation, the root, if it's a same uniform cross section, the root and the tip will have the same angle of attack. So if the root stalls, the wing tip also stalls. But because there is a vortex generation at the tip, the angle of attack seen at the tip is less. So even if your wing root has alpha stall, your wing tip will be slightly less than the alpha stall. Okay, so the wing root experiences the stalling first, which is why you have a twist in the wing, so that at least you can delay the occurrence of stall at the root. Okay. Okay. Yeah. So stall is when the boundary layer detaches. The stall angle of attack is encountered at the wing root first. Okay. Wingtip vortices reduce the effective angle of attack, and the boundary layer remains attached at the wingtip. Okay. So you still have the boundary layer is not completely detached at the wing tips. It happens at the roots. Why doesn't it happen at the tips? Because there is a vortex generation. Okay. Now, if the center of gravity of an aircraft moves towards neutral point, we had just discussed this very simple question. So if your CG is here and neutral point is here. Now, if CG moves towards neutral point, will the aircraft be more or less stable?
Ma'am, less stable.
Yes, less stable. Less stable means stability and maneuverability are inverse. Okay, so if your aircraft is very stable, it becomes very difficult to maneuver it. You need to put in large efforts to control the aircraft, right? Similarly, if your aircraft is less stable, very less stability, it's very easy to maneuver the aircraft because the resistance offered is very less. So when you move your CG towards the neutral point, your aircraft becomes less stable and more maneuverable. Okay, they are inverse. Okay, so yeah, this is just, I will just show you 3 configurations, no questions, just 3 configurations. This is the wing alone configuration. I had told you this mnemonic CAN. So if it is wing alone, you don't have neutral point, you have only CA. So for a stable configuration, your CG should be ahead of AC. This is wing alone. Next, you have wing and tail. For wing and tail, you have CAN. You have neutral point. Your CG should be ahead of neutral point. Your CG is ahead of neutral point. Okay. Now there is a surface called canard. What is canard? This is your wing and this is your tail. What is the canard? Canard is a similar structure which is fixed ahead of your wing. Something behind your wing is tail, ahead of your wing is canard. You may have seen this on some supersonic aircraft. So this again, CAN for a combination A is not this. So CG should be ahead of neutral point for stable configuration. Okay. So I was just showing you the various configurations: wing alone, wing plus tail, canard plus wing. Okay. So in each case, the CG should be ahead of either the aerodynamic center for wing alone or neutral point. Okay. Okay. So with this, we come to the end of this session. Does anybody have any questions? Any doubts? Any questions? We can go over them. Any doubts? We will meet again on Tuesday. That will be before your assignment submission. So you can ask me the questions then as well. But as of now, from today's session, from week 1, any questions?
Excuse me, ma'am.
Yes, yes.
Will you be uploading this recorded lecture on the platform?
Yeah, I will be uploading it. I'll upload it on YouTube and the link will be there on the NPTEL site.
Okay, thank you, ma'am.
And the slides also will be uploaded. That link will be shared with you. Don't worry.
Okay, thank you, ma'am.
Okay.
Ma'am,
Any other-
ma'am, according to the lecture, we want to write the assignment, ma'am.
Yeah, so just go over the assignments, see if you have any questions. Hopefully, I have covered all the concepts necessary for week 1 assignment. If not, you ask me in the next class, which is on Tuesday. Your assignment submission on Wednesday, right? It's on
Yes, ma'am.
Wednesday. So next week, I'll discuss concepts of week 2 and if you have any questions from week 1. So after today's lecture, just see if you can answer the questions. If not, ask me the questions next week or use the forum profusely. We will address your queries from the forum as well. Okay, so put your questions on the forum. Somebody will answer it. Okay, any other doubts? Is the roll to starboard side considered positive? Okay, so we have not dealt with that convention yet. So let me see. Roll towards the right. Yes, that is considered positive. Correct. Right is the starboard. So roll towards the right would be right aileron up, left aileron down. It is considered positive. So what are the conventions? I will just discuss with help of this figure. Yeah. So put your thumb along each of these axes and the motion of your curl of your fingers gives you the positive motion. So we had discussed pitch now. Put it along the pitch axis. Pitch up is considered positive, right? Similarly, put it along the roll axis. So roll right, roll towards starboard is considered positive. Again, yaw towards the right is considered positive. So that is how the convention is denoted. Okay, so put your thumb along the axis. The direction of your curl of the fingers gives you the positive convention. Okay. Any other questions?
Ma'am, how to attend the assignment, ma'am?
How to attend the assignment? Have you gone over the questions? Just mark the things, mark the options. You have multiple choice.
Not like that. How to find out the assignment thing in the session means web, ma'am. I'm not aware the NPTEL, so that's why I'm asking.
Oh, okay. So on the site, you want to know where the assignment is?
Yeah, ma'am.
Okay, just a minute. I will stop sharing this and I will 1 minute. Okay, so can you see my screen? Can you see my screen?
Yes, ma'am. Yes, ma'am.
Okay, so this is the main page, which the announcements. Okay, so on the side you can see the course outline. So you have week 0, week 1, week 2. Week 0, there were some practice questions. It is not graded, so you can just go over it in practice. Week 1, at the end you have quiz. Can you see that? Quiz assignment 1.
Yeah, yeah.
Just click on that and submit your options. So these are the questions. Just click whatever answer, and then at the end you have submit answers. You can do it anytime before 2nd. Anytime before, what was the deadline? Yeah, anytime before 9th. So we will meet again once before 9th, so you can ask your queries then. But is this clear? Now you know where to find out the quiz, right? Go to the home page, click on week 1 quiz. Before that, go through these lectures, lecture 1, 2, 3, 4, 5. Okay.
Okay, ma'am.
Okay. Yeah. Any other questions?
Nothing, ma'am. Go to the quiz and select the options and submit, ma'am. That's it, ma'am.
Yes. That's all. That's all.
Okay, ma'am. Thank you.
Thank you. Anybody else? Any other questions? Okay, if there are no other questions, then we'll end the session. We'll meet again next Tuesday. Okay, thank you.
Thank you, ma'am.
Do your assignment well. Thank you for joining.
Bye.